Hi there, this video is to look at complex ions and how it affects the solubility, in other words we're going to do some math with it, of any soluble salt. So complex ions are really just that, like complex ions. Like take a look at silver chloride. We know that it's partially soluble. It's got a very low KSB, so not much dissolves. We usually call it insoluble. But what can also happen is we can force it to be more soluble if we add an ion that it likes to be with. So in other words, if I want to add and make this into a solution of ammonia, aqueous, it's an aqueous solution of ammonia, the silver ions, which are right here, will actually connect with the ammonia to make this complex ion. So what it does is it actually dissolves more of the silver chloride than would have normally been dissolved. Let's look at it from Le Chatelier's principle. You've got this established in equilibrium, this top equation. Suddenly, you're going to take away the silver ions. You take away the silver ions by adding NH3. NH3 and the silver ions now hook up together to make this ion. So it's as if you don't have any Ag plus by itself. Well, Le Chatelier's principle says that's not okay, so it'll shift, in other words proceed to make more products, and some of the solid will now become aqueous. In that way you can actually dissolve more solid by having it in the NH3 solution. So how do we do math with that? Well, let's take a little bit farther at this complex ion thing. Here's a table. If you look in your textbook you'll see this table too, of a bunch of complex ions. AP specifically says you don't have to memorize any complex ions, but that's not to say that they're not going to show you those type of equations. Things to know about complex ions is that they're complex ions, and take a look at all their KFs. Those are like 10 to the 42. Oh my god, 10 to the 29. These are humongous numbers, which means the KF, this is a formation constant when you do with complex ions. The formation constant, in other words, the formation constant, how likely are you to make these products? Extremely likely. The KF is so high. So that comes into our math plane. Let's take a look at the question. Here we go. Okay. So these ones are a little weird. Okay. Calculate the concentration of Ag plus present in solution at equilibrium when a concentrated solution of ammonia, so that's exactly the example I was kind of talking through, what happens with the silver. Okay, so the first thing that I want to look at is actually the KF they give me. So I'm going to write the complex ions, equilibrium expression, and the equilibrium equation. Now this one, like I said, AP doesn't expect you to memorize these things. They used to, but they don't anymore. And they would have to give the equation. So I will always give you the equation, and the textbook would too. So really we're looking at a silver ion with NH3. In fact, we need two of them, because, whoop, I should make this big and this little. It's going to make the complex ion of silver, this should really be a parenthesis, with NH3, two of them with a positive. Okay, whoop, there we go. Okay, I'm going to write my KF for this. Notice that it is aqueous, that complex ion. Those complex ions are, they're not solid situations, so we do need to include them. So my KF is going to equal Ag NH3 2 concentration ion, so I do need that plus side. Ag ions, NH3. Okay, looking good. And my KF is that number. Okay, this is a little tricky. I'm going to make my ice table. When in doubt, ice table is always a good way to go. But I also know that's going to have there because it did talk about equilibrium concentration. We did have an Ag present in equilibrium solution, and then concentrated ammonia is added to it. So I know this is an ice table situation. But what it actually is kind of saying is you had equilibrium of the Ag, and then you added the ammonia to it. So remember with these two equations here, it's kind of like you have two kind of ice tables set up in a way. Oh, go away. So we have like this top equation kind of in equilibrium, and then you're going to steal away the silvers and you have this bottom equation. So it's kind of like you have two equations. You technically have two ice tables, which makes it really complex. But we can simplify it down by really just looking at this equation because it's what's driving the changes. The fact that the KF is so large is what's driving that silver to go away, and it will in the end control how much silver ions are in solution. Okay, so that's why I only need to look at this equation. The first thing to notice is that I've got a 0.01 molar solution of silver nitrate. Now normally, I say normally because it's not going to stay that way, now normally I'm putting in yellow, we would say that the silver ion concentration is 0.01. But what I'm saying is that it's 0.01, yes, but the moment you add NH3, look at this KF. It's freakishly large. 10 to the 7th is pretty large. Not as freakishly large as the other one, but it's large. So what that means is this actually isn't silver anymore. It quickly fully shifts to make all product. If you think back to that AP question that we did before the last quiz, we were looking at a big Ka, or it wasn't a Ka, a big Kc, and it showed that it goes to completion. That's what's happening here. So I'm going to really say that there's 0.010 of this ion, because I had all the silver, I added a large amount of NH3, and it fully made all of this stuff here. Okay, so I'm starting actually with this here. Weird, I know. So it all goes to completion, and then it starts to think about its equilibrium. Some of this is going to go away, and some of this is going to be made. Now, this technically is going to be made too, but what we got to note is that it says NH3 is 0.2 molar in equilibrium. So this is 0.20 molar. So what that's really saying is whatever this is right here, the shifting is going to be enough. Whatever kind of shifting you're going to do, you're going to have a lot of this that you're going to add in to the solution. And some of it is going to kind of go all the way to make this 0.01, but you have so much in there that at equilibrium you still have 0.2, which really tells you it doesn't really matter what's happening with the changing, because it tells you the equilibrium concentration, and that's what really matters, because that's what we put in the KF. So what's happening at the molecular level is you've got silver ions, you had them at 0.01. You dumped in a bunch of NH3, whoop! It went to completion, the limiting reactant was the Ag, and we made all the Ag NH3 complex. Then it kind of shifted back, and I got 0.2 molar NH3. So I really don't know how much NH3 I actually added. I could calculate that, but that's not the question here. But I do know at equilibrium I had 0.2. So really, this in-betweeny stuff doesn't matter all that much. It's weird, I agree, but that's how we roll. Okay, now let's do like normal math. So now, adding up I and the C, got X. Taking here is 0.010 minus X. Boop-a-doop. Okay. So now I can kind of plug and chug this into my KF. I'm going to do a little sidestep quick here because it's going to head down quadratic equation land. Anytime you have this minus X kind of thing, it heads that way. So I'm going to assume between the two, I got X and 0.01. I'm assuming that X is much greater. Wait a minute. Nope. I had to think that through. Sorry. I can't say that X is much greater. Whoop. Try again. The KF is really big, which means I have a lot of products. Which means I'm not going to have many of them shift back. X is much smaller than 0.01 because the KF is large. Okay. So now that I know that, I can assume that X is really kind of negligible. Whoop. We don't really need it. We really should have like about 0.01, maybe a little bit less, but sig fig wise, we can assume it's going to be 0.01. Now I can put my numbers into KF. 1.7 times 10 to the 7th equals, top number is 0.01, bottom number is X, this is 0.2, squared, whoa, I lost that squared. This is squared because this 2 right here. Whoa, almost lost that. Okay. So now I can do my math, I can solve that X is equal to, where is my answer? Whoop, here it is, 1.5 times 10 to the negative 8 molar. There we go. That's like my end answer. It says, calculate the concentration of silver ions present in equilibrium after all this stuff is done. Boom. Here's X. Here's X. I do want to check my assumption here, because I did assume that X is going to be much smaller than 0.01. So it's 1.5 times 10 to the negative 8 divided by that 0.01. Is that going to be less than a 5% error? Oh yeah, it's definitely less than a 5% error, so I'm totally good there. So that's the end answer. The tough part is making this ice table and figuring all that stuff out. So I hope that worked for you. Good luck.